Okay, for second derivative, okay, point of inflections. Okay, so we start talk about second derivative first. If you can quickly go to page 12, let's have a look at some diagram first. I think this is the diagram I get from the textbook. Okay, so what second derivative really represents? Okay, what second derivative represents? Sorry. Sorry, just wait a second, I find a paper for her. You can enter 4 minutes, and then I can come back. I may forgot to 25 minutes. Yeah. Okay, so what second derivative really means? If you think about first derivative, let's read graphs in rows. Okay, let's read graphs in rows. So the first row, all the graphs is increasing graph because from left to right is increasing. So that's first derivative greater than 0. Second, first derivative less than 0 is this row. Okay, second row is all decreasing graph. And like when the points have derivative equals to 0, they are stationary points. Okay, we learn from methods. There are two types of stationary points: turning point and stationary point of inflection. Okay, so turning point got maximum turning point and minimum turning point. I remember in method we draw the table to decide whether it's a maximum or a minimum. So we have a better way now. And then we have like stationary point of inflection. We have like kind of increasing and decreasing stationary point of inflection, but they really look the same. That's the first derivative. Okay, if you look at in rows, we are talking about first derivative. Let's talk about second derivative now. So if you think about second derivative greater than 0, okay, second derivative greater than 0, this means concave up. Okay, so what's concave up? Is for this part of the graph, when you draw the tangent to any point of this graph, you will have the tangent below the graph. Okay, look at all these tangents. Is that all the tangent below the graph? Doesn't matter whether it's increasing function or decreasing function. So that means concave up. So concave up means for any, like for this part of the graph, you sketch the tangent at any point of this graph. You will have the tangent below the graph. Okay, you have the tangent below the graph. So if you draw the tangent here, it's still below the graph. This concave up means, okay, so concave down is second derivative less than 0. Okay, second derivative less than 0. Second derivative less than 0 means is concave down. Okay, so second derivative less than 0 is concave down. Oppositely, like if we have this part of the graph, we sketch the tangent at any points. You should have the tangent above the graph. You guys should have the tangent above the graph. Look at all these graphs in the second column. Doesn't matter it's increasing, decreasing, or stationary. They are like below the graph, above the graph. The graph is below the tangent. Okay, so that's concave down. And well, second derivative equals to 0. Yeah, second derivative equals to 0. It's not quite true. Okay, so let's assume it's true. Second derivative equals to 0 here. We will have point of inflection. Okay, it's different from a stationary point of inflection. What's a stationary point of inflection look like? It's like that, the last one. Okay, so in the last graph, the first derivative equals to 0 and second derivative equals to 0. So basically, what's second derivative equals to really mean is when you draw the tangent at that point, you separate the graph into two halves. Like one is on the left hand side and the other half is on the right hand side. Look at all this tangent. You cut the graph. It just cuts the graph. Like the tangent will cut the graph into two halves. Okay, but there will be only one point like that. It's not like for these. Okay, for these four, there will be a part of like range, like say from 0 to 4, like it's all concave up from 0 to 4. So it's talking about the range of like x values. So it doesn't matter how you sketch the tangent in between 0 to 4, the tangent is above or below the graph. But for equals to 0k, okay, for equals to 0k, it's actually at that point. Okay, at that point, we have this property. Okay, we cut the graph into two halves, and one is above and one is below. So that's really what the point of inflection means. Okay, if you ask me what's the point of inflection looks like, the point of inflection will look like this. Okay, Okay, so when you draw the tangent at point of inflection, you should cut the graph into two halves. Okay, you should cut the graph at two halves. So let up and down. Okay, so one is above the tangent, one is below the tangent. And the stationary one is just the tangent is actually horizontal. So look at this one. This one still cut the graph into two halves. One is above and one is below. And it's still, okay, still like second derivative equals to 0 in this case. But another thing is first derivative equals to 0 as well. Then that becomes a stationary point of inflection. Stationary point of inflection is part of point of inflection. It's a special one, just with the tangent is a horizontal tangent. Okay, so that was really the meaning for second derivative. Okay, so it's the meaning for second derivative. All right, now we can have a look. If your first derivative equals to 0, well, let's continue talking about this from method. Okay, from method. If we look at first derivative equals to 0, the last row, okay, the last row. I don't want to draw the table anymore. Like it takes me too long to decide like whether it's a turning point or point of inflection or stationary points. So I will just talk about the second derivative. Well, I solve out my first derivative. Let's say this point is 3, 4. For example, it's 3, 4. So I know this point now. I know it will be a stationary point, but I don't know whether it's a turning point, maximum turning point, minimum turning point, or stationary point of inflection. I will sub this point into second derivative. Okay, I'll put the value into second derivative. If second derivative greater than 0, it will be a minimum point. It will be a minimum. Why? Second derivative greater than 0 is concave up. Think about concave up. That will be a minimum point. Okay, concave up. Your tangent is below your graph, and that must be a minimum point. Okay, concave up means like this way. So you have a minimum point there. So if it's second derivative less than 0, is maximum because it's concave down, like it's this way. So it must be a maximum point. Okay, so it's opposite. When it's bigger than 0, it's concave up, then it's a minimum point. When it's less than 0, it's concave down, and then that's a maximum point. Okay, that's the two different cases. When you get second derivative greater than 0 or less than 0, that will be good. Okay, it saves you a lot of time. But if you have second derivative equals to 0, we can't make any decision. Okay, we can't make any decision. Second derivative equals to 0, you can't make any decision. So we'll go back to page 12. Look at all these things. We don't need to worry about everything like above. You can read through it. That's basically what I just repeat. Okay, so what I just said is all the paragraph above. So you can read them and make, like if you forget, you can go back to read that. But look at the 4 points, 1, 2, 3, 4. Okay, look at those 4 dot points. That's the thing you need to remember. Okay, the top part is explanations, and this 4 is the thing you need to remember. If first derivative equals to 0 and second derivative greater than 0, you have minimum stationary point. Okay, that's what I just said. First derivative equals to 0, second derivative less than 0, that's a maximum stationary point. Okay, that's the two things we talk about, and that's what you need to remember. Number 3 is important, and everyone needs to pay attention to step number 3 and step number 4. We only need 2 conditions to make conclusion that whether it's a maximum or minimum stationary point. But I need 3 conditions to talk about is the stationary point of inflection. First of all is the first derivative must be 0. And the second derivative must be 0. Okay, think about the graph we look at the last corner, right hand side corner. But there's a third condition, and you must follow that one, and you must check it. That is second derivative change sign at x equals to a. What's second derivative change sign? Yep. So that's the second derivative. So your a is here. Left hand side and right hand side must change sign. I'll give you a counter example when it's not the stationary point of inflection. What's y equals to x to the power 4 looks like? That one, right? And what's the second derivative? Well, first derivative looks like? What's first derivative? dy dx, 4x cubed. So I'll have this one, kind of. Okay. What second derivative looks like? 12x squared. Do I have first derivative equals to 0 and second derivative equals to 0 at 0? Yeah. And do I have a stationary point inflection on my original graph? No. Okay, so the third condition is essential and is necessary to check every time. Okay, so this is just an easy counterexample. X to the power 4 is not a stationary point inflection. And I get first derivative equals to 0 and second derivative equals to 0. But it doesn't change sign at the point 0 on your second derivative. And then it can't become stationary point inflection. Can't. We can't. Like we can't x-axis like that. But it can be cut. Like it can go up and down, like or the other way. Yeah, like positive on the left hand side, negative on the right hand side, or the other way around. Yeah, it's an x-intercept, and it can't be a like turning point kind of intersect. It must be like a strict like cut intersect. Okay, so I'll talk about how to test it later in the next example. But that's something you must remember. Okay, something you must remember. Um, and what's a point of inflection? Point of inflection is more like bigger, like I don't need to be like stationary now. So basically point of inflection, I'll add a condition here, well, it's not really necessary. Is first derivative not equals to 0? Okay, I would say that's my first condition. Or not really necessary. Stationary point of inflection is part of point of inflection. But if I really want to distinguish that, like I would say first derivative not equals to 0, but second derivative equals to 0. Okay, only second derivative equals to 0 at that point. And again, it needs to change sign at that point. Then it can become a point of inflection. Otherwise, it's not a point of inflection. Okay, so if only second derivative equals to 0 but doesn't change sign on the x-axis, then it won't become a point of inflection. Well, I can't really show like graph this one. Like I tried to find one last time, but I forgot the equation. It's like quite complex. But like it's true. Okay, I can find one another next time. I'll show you on the test. Only second derivative equals to 0 is not enough to say it's a point of inflection. It can be just nothing. Okay, it can be just nothing. Like it's not any special. And so you must satisfy first derivative not equals to 0, second derivative equals to 0, and change sign. Okay, and change sign. So change sign is very important for first derivative. I can't remember what I want to say. If you're hot, just turn on the aircon. Okay. So now let's just look at example 11. Just look at example 11. I'll show you the steps to talk about points and like stationary points, cost deflection, all that kind of thing. Okay, so this graph we know how to sketch it. That's a polynomial graph and it's an easy graph. I know everyone can sketch. But let's assume it's something we don't know. Okay, so something we don't know. We're not familiar with this graph and we don't know how to sketch it. So what I will do is step number 1. Okay, to sketch any unfamiliar graph, step number 1 is, well, step number 1 maybe find x, y intercepts. That's the first thing you want to find, or any asymptotes, but that's in general. If you talk about like in derivatives, what we can do, the first one is find f dash x and make that equals to 0. Second one, so second derivative and make that equals to 0. Third one, draw a second derivative table. And I'll show you what to do with those 3 steps. Find y value of coordinates, like of these coordinates. And state nature. Okay, that's basically the 4 steps. Okay, using these 4 steps is easy to find all the points. Okay. I'll just slowly do the ideas. I'll just use a really easy one. So what's the idea? The idea is 12x squared minus 4x cubed. Okay, that's 5 divided by x. So I will take 4x squared out. So it goes 3 minus x. That equals to 0. Okay, first derivative equals to 0. So I have to solve out 2 points. X equals to 0 or x equals to 3. So what those 2 points could be? Stationary points. Can be turning points, maximum, minimum, or it can be stationary point fraction. Can't make conclusion yet. Okay, I will just leave it here. That's the 2 things. I will come back to it later. So those 2. Okay, then I will be interested in the second derivative. Okay, what's second derivative? 24x minus 12x squared. Okay, I'll take 12x out. 2 minus x equals to 0. So we second derivative equals to 0, f x equals to 0, or x equals to 2. Up to here, can I make conclusion x equals to 0 is the stationary point fraction? Yes or no? No, I need to test the sign. Okay, I need to test the sign on both sides of 0. So that's why I will say draw second derivative table. Do you remember how you draw first derivative table last year? Last year, first derivative. Like, I would do the second derivative, but there's something like, you can put some easy things, like, let's just try to do it. So we have 2 points. So I can use 2 rows actually. F dash dash x. So first one empty, and I'll put 0 and 2 in. So 0 and that's empty. Next one. 0 and 2 is the 0 x-intercept on the second derivative graph. And I know that second derivative equals to 0 for those 2 parts. All right, which is another, like, say on the right hand side of 2, which value you put? I will put 3 because 3 is something I really want to test. If I have 5, I'll put 5 there because that's the point I want to see the second derivative to test whether it's a maximum turning point or minimum turning point. So anyway, we need to find second derivative of 3. So directly sub that in, save me some time. I can just pick a 1 and negative 1 here. Okay, let's test the point 3. Let's put 3 into second derivative. Okay, it's the second derivative. So in order to rather use that one, I would just maybe use this one. That's in the factorized form and easy to see the substitution. 12 times 3 is positive. 2 minus 3 is negative. So this point is a negative value. I don't really need to calculate that out, but I can just see it's positive or negative. So when I sub 3 in, I have negative. When I sub 1 in, do I have positive or negative? Second derivative. Okay, don't stop in the wrong one. Positive. And how about negative 1? Negative 1 is negative. All right. The 3 points I read in blue pen is the 3 points I'm interested in. It's either so first derivative equals to 0 or second derivative equals to 0 or both equals to 0. Okay, that's the 3 points I really love to see. So the conclusion I can make here is, okay, how about 0? What conclusion is it to make for 0? First derivative equals to 0 and second derivative equals to 0 and the change sign on both sides. You can see negative and positive. So it's stationary point of inflection. Okay, stationary point of inflection. What do you guys say about the point 2? Is that stationary? It's just a point of inflection. It's just a normal point of inflection. It's not even stationary because first derivative it doesn't equal to 0, and only second derivative equals to 0. And change sign on both sides. Okay, positive and negative. Positive and negative. How about 3? Good, maximum turning point, maximum turning point. Okay, second derivative is less than 0 is definitely a maximum turning point, and plus is first derivative equals to 0. Okay, first derivative equals to 0, first derivative equals to 0. Okay, so negative second derivative will give you a maximum turning point. 0 is when you change sign on both sides of second derivative, it will be a point of inflection. And then for the 0, first derivative, second derivative both equals to 0 and change sign on both sides, so it's a stationary point of inflection. Any questions? And you can find the coordinates. Yeah. Because first derivative of 2, first derivative won't give x equals to 2. So stationary point only exists when x equals to x. It's your first derivative equals to 0. When x equals to 2, first derivative doesn't equal to 0. So it can't be stationary. Which one? The local maximum. I can say a local maximum. Okay. All right, everyone. Hello. Hi. Example 12 is exactly the same thing. You can just do that by yourself later. And if you go to example 4, let's look at page 13 and then look at example 14. Example 14. Okay. What's f dash x for this function? What's f dash x? 2x times e to the power of x to the power of 2. Okay, that's my f dash x. What's second derivative? Okay, we derive 2x first. We have 2e x to the power of 2. And then we derive this one. That's 4x squared e(x) to the power of 2. Well, when you do exponential derivatives, I would recommend you always take common factors. If you can see that, normally the e to the power of something will be the common factor, because when you did that, you still repeat the function again. So you always get this down. So I will take a common factor here. Okay, that's this one. I can take this one as well. Yeah. 2, 1, and squared. Yep. Okay. Solve the equation f dash x equals to 0. How to solve that equals to 0? So x equals to 0, or can I have this equals to 0? No, this is always positive. E to the power of x is always positive. The graph is like that. The x squared, well, x squared will make like something like that. The graph is kind of like this. But you don't need to know how to sketch that. So x equals to 0 is the only solution. Okay, only solution for stationary points. Okay, show that f dash dash x greater than 0 for all the x. That's a 4. For all x. How to show that? Huh? What? One part. Yeah. So I can say that greater equal to 1, right? Can I say that? Yeah. Well, I can say greater equals to 0, like it will be the same. So I just want to say greater than 0. So I can change that to 0, no problem. It's true. Okay. This equation is square, always positive. And 2e x to the power 2 is always not greater equals to always greater than 0. I would say that's greater than 0. So two positive numbers times together is always positive. So that's why the second derivative is always positive. What that shows you, what second derivative always positive means? What that means? Tangent is always below the graph. It's always concave up. Okay, it's a concave up graph. So the whole graph is concave up. Okay, say the intervals for which fx is increasing. So which part of the graph is increasing? Not all. Fx is increasing. Increasing or decreasing, you still need to go back to first derivative to look at it. Yeah, so second derivative doesn't tell you increasing or decreasing, only tells you concave up or concave down. So you only want to see first derivative to decide whether it's increasing or decreasing function. So for increasing function, what do I need? I need f dash x to be greater. I can say equals to 0 as well. To remember increasing function, you need to include the turning point as well. Do you remember that? Can someone like just stop talking for a while? It's just, I really can hear a lot of noise. Not really talk about math questions. It's hard to talk over you. Okay, so first derivative greater or equal to 0, because remember when we say which part of the graph is an increasing function, we do include in the turning point. And then we start from the turning point to infinity is a decreasing function. So the end, like the turning point will be included in part of the increasing or decreasing function. So twice. And that's something we learned in method last year. So first derivative greater or equals to 0 will be increasing function. So I would just say x greater or equals to 0. Because you know like that's 2x times e to the power of x to the power 2 greater or equals to 0. That part is just a greater than 0 number. It's a positive number and I can just divide it on both sides. Then I just have 2x greater or equals to x equals to greater or equals to 0. So decreasing function is just x less than or equals to 0. Okay, so you will have a turning point at 0. I want to ask you, at the point 0, is that a maximum point or a minimum point? Definitely can't be a stationary point now. Because like second derivative is always greater than 0. How do you get it? Yep, second derivative equals to second derivative. Okay, great. Like wait, what's second derivative? Where's my second derivative? Here. So second derivative is here. So it's 2e to the power of 0 times 1 plus 0. And that is definitely positive. So it's true. It's always positive. Second derivative is always positive. So that's a minimum point. Minimum turning point. Okay, so the point 0 is the minimum turning point. If it's a challenging thing, try to sketch this graph. Okay, by all the information we have here and try to think about what this graph will look like. Okay, it's not really necessary. Like we don't really sketch this type of graph, but with all of this information is enough to think about the shape of the graph. So trying to think about that. Yep. We are intervals between -1. I can make it longer. Like I can make the interval like longer. It doesn't really matter. All right. You sketch this graph by yourself. There are some practice questions here, and I will show you a question now on the board. And you can see that's a VCA question, and that's related to this one directly. Trying to think about that one as well. I'll stop my recording here first.